Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back. Today we are strapping in for a journey that takes us, right back to the first fractions of a second of the universe, all in the service of solving cosmology's most persistent and, I think, most infuriating mystery, dark matter.
It really is. It's the ghost that runs the cosmos. I mean, when you look at the fundamental composition of reality, the numbers are they're staggering. Roughly 85% of all the matter in the universe is dark matter.
85%.
Oh.
It's hard to even wrap your head around that. It's the invisible foundation that everything we see is built on. All the galaxies, the stars, nebulae, the huge superclusters. That's just the tip of the iceberg, the remaining 15%.
And yet, that 85% is a complete enigma. We know it's there. We can see its gravitational influence everywhere we look.
Yeah.
But it just refuses to interact with normal matter through any other fundamental force.
We can't see it, we can't taste it, and after decades of trying, we certainly can't seem to catch it.
And that elusiveness has created, a decades-long crisis in particle physics and cosmology. We have built these enormous, incredibly sensitive detectors deep underground, all looking for this phantom, and those searches just keep coming up empty.
Which is why our mission today is to dive into a fascinating new piece of research. And it asks us to look backward, not for a new kind of particle, but maybe for a new timeline.
Exactly. The source material is a paper that was published in Physical Review Letters, led by Stephen Henrich and Keith Olive. And it's a bold proposal because it doesn't invent some new exotic particle. It actually recontextualizes an old, discarded theory.
Okay, so this is about unpacking their idea, which suggests a faster, earlier mechanism they call Ultra-Relativistic freeze-out could revive a candidate that's decades old.
Right, and the brilliance is that this one single shift in time potentially solves two of cosmology's biggest, seemingly unrelated hurdles all at once.
Okay, what are those two hurdles?
Well, first, it explains why we haven't found dark matter yet. It suggests its interaction strength is just too weak for our current detectors, which were mostly built to find WIMPs. And second, and this is the crucial part, it validates how galaxies even managed to form in the first place. It resolves the fatal flaw that killed the original version of this theory way back in the 1980s.
So the core innovation, the real tease here, is that the problem wasn't the type of dark matter particle they first theorized back in the 70s. The flaw was the assumption about when that particle was created and when it decoupled from everything else.
Yes. We're moving the clock back to the earliest possible moments, and that single revision changes everything about how the particle behaves over cosmic history.
It's a masterclass in theoretical physics, really. The history of the universe is just this sequence of events happening at precise temperatures and times. And by finding the one moment where an existing mechanism actually works, they might have bypassed decades of, dead ends.
We are literally scrutinizing the physics that define the cosmos at, 10 to the power of negative 32 seconds. It's mind-boggling stuff.
Okay, so to really appreciate the elegance of this new proposal, we have to start where the original idea failed. We need to go back to the 1970s. This was the first serious attempt to identify the particle that was providing all this missing gravitational mass.
So what was the original candidate, and why did it seem so plausible at the time?
The initial candidate was, surprisingly elegant. It was just neutrinos.
Neutrinos. Okay, that makes sense. They're everywhere. They're tiny. They have no charge, and they are definitely part of the standard model. We know they exist. We know they have mass, even if it's incredibly small.
Exactly. And that's what made them so attractive. You didn't have to invent any new physics beyond the standard model.
Right.
We knew they interacted extremely weakly with other particles. I mean, they screamed through the entire Earth without stopping, which definitely satisfies the dark requirement.
The idea was that the early universe was so hot and so dense that these particles were, for a very brief time, in what's called thermal equilibrium with the rest of the cosmic plasma.
So even though they're famously weakly interacting, they were still interacting all the time back then because everything was just so crowded.
Yeah.
So tell us about the mechanism that eventually separated them, this hot freeze-out.
Hot freeze-out is a thermal process. It happens when the universe expands and the temperature drops to a certain point. a point where the interaction rate of a particle becomes slower than the rate of the universe's expansion.
They just can't find anything to interact with fast enough anymore. They get left behind.
They get left behind, exactly. And this would have happened during the radiation-dominated era when temperatures were still immense. So when these neutrinos decoupled, they kept their extremely high kinetic energies.
And high kinetic energy translates directly to their speed.
It means they were moving at ultra-relativistic speeds. So right at or extremely close to the speed of light, they freeze out, they decouple, while they're still extremely hot in a cosmological sense. And that's where the name comes from. Ultra-relativistic freeze-out, or UFO.
Okay, so the 1970s theory was simple. Dark matter is just a neutrino that decoupled during the standard radiation era. It fits the mass requirement, it fits the dark requirement. So why did this theory completely collapse in the 1980s? What went wrong?
It collapsed because of what cosmologists call the cosmological catastrophe of the hot dark matter model. More detailed calculations revealed that if the dark matter decoupled at those speeds during that era, it would have fundamentally prevented the formation of structure as we see it today.
The infamous density smoothing problem.
That's the one.
So this fast movement, it's like a cosmic blender effect. How does it actually stop gravity from being able to build things?
Right. You have to think about the scale of things here. How do galaxies form? They start from these incredibly tiny seeds, these microscopic fluctuations in the density of the early universe. Anisotropies. You see them perfectly in the cosmic microwave background. You need these slightly overdense regions for gravity to grab onto and pull more matter in.
But if the dark matter is hot and moving incredibly fast,
it means it has a very long free streaming length. The free streaming length is basically the distance a particle can travel freely before gravity can effectively trap it. If the particles are moving at ultra-relativistic speeds, that distance is enormous.
So the dark matter is moving so fast it just zips right out of those initial small pockets of higher density. It doesn't stick around.
Precisely. It escapes. So if your dark matter has a very large free streaming length, it prevents the clustering of mass on small scales, the very scales you need to form the initial seeds of, say, dwarf galaxies or the first star clusters. Instead of building structures, the fast-moving particles just spread their energy out, smoothing away those critical density fluctuations.
So the implication is that hot dark matter would only allow for the formation of really, really big structures, like superclusters, and much later in cosmic history. It would suppress the small stuff from forming first.
And that's the key. That's the complete opposite of what we observe. Observations show that structure in the universe is hierarchical. Small things formed first, then they merged to form bigger and bigger things. The 1970s hot dark matter model predicted the reverse. It was fundamentally incompatible with the universe we live in.
So the ultra-relativistic freeze-out mechanism, as it was originally understood, was just off the table, dead in the water.
And that failure forced physics onto a completely new path. It led us away from known particles in the standard model and toward theoretical ones that sit outside of it.
This is where we get the shift in thinking.
It was a necessary pivot, really. If dark matter couldn't be fast and hot, then the thinking was it had to be slow and cold. And that led to the dominance of alternative candidates, primarily the WIMPs.
WIMPs. Weakly interacting massive particles. And the massive part is crucial here, right? Because massive implies they're slow or cold, which would preserve those small density fluctuations.
That's the theoretical mandate. WIMPs are hypothetical particles, usually much heavier than a proton, and their interaction strength was predicted to be within a range we could actually detect with large-scale experiments. And crucially, they are produced via a different thermal mechanism, just called thermal freeze-out, the canonical dark matter scenario. They're heavy, so they're moving slowly, non-relativistically, and that keeps their free streaming length small.
And WIMPs have defined the search for decades. We've built these incredible detectors, LUX, Xenon, Band-X, deep underground, just waiting to catch one of these particles bumping into a detector nucleus.
The search has been exhaustive. We've been looking for WIMPs in this predicted mass range of, tens to hundreds of JeV, and the results have been consistently null. The Xenon 1T experiment, for instance, set extraordinarily tight limits on the interaction cross-section for these particles, limits that rule out huge swaths of the original WIMP parameter space.
So if WIMPs are even more weakly interacting than we thought, we get into the realm of FIMPs, right?
Yeah.
Feebly interacting massive particles.
Right. FIMPs represent the non-thermal production regime, often called freeze-in.
Yeah.
These are particles that interact so feebly they never even reach thermal equilibrium with the early universe. They're produced very rarely, just from random collisions of standard model particles. They are the definition of elusive.
So we have a crisis. The original hot dark matter, neutrinos, destroys structure. The cold dark matter, WIMPs, should be detectable, but they aren't. And FIMPs are so feeble we can barely even figure out how to look for them.
And that impasse is the core motivation for Henrich and Olive to go back and revisit the past. They're asking, what if the whole WIMP-centric search was flawed? Not because the theory was wrong, but because of a historical oversight about cosmic timing.
It's the ultimate expression of scientific humility, isn't it? Instead of just inventing another new theoretical particle, they went back to that moment of failure in the 1980s and asked,
what assumption did they make about the timeline that we now know could be different? And the answer, they argue, lies in the very earliest cosmic era, the moment of reheating.
Okay, let's get into it. This is where we tackle the Henrich and Olive proposal. Ultra-Relativistic Freeze-Out 2.0. The core idea seems simple in concept, but it's radical in its execution. They move the whole process significantly earlier, placing it right after cosmic inflation in what's called the reheating era.
And that shift is everything. It changes the entire environmental context of particle creation. In the original 70s theory, decoupling happened in the established radiation-dominated era, where the universe was already this well-mixed soup of particles. This new setting is the tumultuous, incredibly brief moment when that soup was first being brewed.
To really understand why this matters so much, we need to map out the cosmic timeline right at the very beginning. Let's start with inflation. What defines that period?
Inflation is the standard paradigm for the universe's first moments. It was a period of exponential expansion, happening almost instantly, maybe from 10 to the minus 36 to 10 to the minus 32 seconds after the Big Bang.
Wow.
During that period, the universe wasn't dominated by matter or radiation. It was dominated by the potential energy locked in a single quantum field, which we call the inflaton.
So the inflaton field is what's driving this insane expansion, blowing up the size of the observable universe by factors of, 10 to the 26 or more in the blink of an eye? Yeah.
Exactly. And that energy was vast. But because the expansion was so incredibly rapid, the universe became extremely cold. The energy density was stored in the field itself, not in the kinetic energy of particles. So inflation solved huge problems, like the horizon problem and the flatness problem, but it left the universe functionally empty and cold.
Which just brings us directly to the crucial new timing element.
Yeah.
The reheating period. So what happens when inflation ends, and why does this period, as Henrich puts it, radically alter the way that dark matter production occurs?
The reheating period is the great energy conversion. Inflation ends when the inflaton field starts to oscillate around the minimum of its potential. And these coherent oscillations are unstable. They decay.
They decay into what?
They decay into the standard model radiation particles. This process is what creates the hot, dense plasma we traditionally associate with the early Big Bang. It literally reheats the universe. And that sets the initial temperature that kicks off the radiation-dominated era.
Okay, so this is the very first moment that standard model particles are even forming. And this is where Henrich and Olive place their ultra-relativistic freeze-out.
Precisely. Their key insight is that the ultra-relativistic dark matter particles decoupled from the standard model particles. At the same time, those standard model particles were first being created out of the decaying inflaton field.
That sounds incredibly chaotic.
Yeah.
How can decoupling even happen if the particle soup is still in the process of being made?
Well, the mechanism is a bit different from the standard thermal freeze-out that we talked about for WIMPs or the 70s neutrinos. In that standard scenario, the particles are already in equilibrium and then they decouple. In the reheating era, they're produced directly from the inflaton decay and immediately start scattering into the brand new standard model plasma. They have this very short window of interaction before the rapid expansion, and the whole thermalization process just pushed them out of equilibrium.
So it's like a thermal process, the ultra-relativistic freeze-out, but it's happening inside a fundamentally non-thermal context, which is reheating.
That's a perfect way to put it. That's exactly the conceptual bridge they're building. They're linking the thermal past to this non-thermal era. The UFO dark matter particles are produced hot, meaning they have very high kinetic energy, but their production rate is tied directly to the dynamics of the inflaton decay. And that happened at an astronomical temperature, the reheating temperature.
And this early timing, placing it in the reheating era, is the solution to that 1980s density smoothing problem. It seems counterintuitive, though. If the particles are still born hot and ultra-relativistic, how do they suddenly become cold enough to allow galaxies to form?
because of the massive time difference. In the 1970s model, the particles decoupled much later, say at a temperature around 1 MeV, and they stayed hot for a cosmologically significant amount of time, destroying small structures.
But if they decouple right at the end of inflation at some insane temperature, like 10 to the 10 GeV or even higher,
you grant them an immense amount of time to cool down. The decoupling happens so early, and the subsequent expansion of the universe is so rapid that even though they are ultra-relativistic when they freeze out, the subsequent cooling during the entire radiation domination period is enough to drop their energy significantly.
it's like sending something through a very, very long cosmic freezer immediately after it comes out of the oven.
A very effective freezer. The kinetic energy just drops because of the Hubble expansion. So by the time the universe reaches the epoch where gravitational collapse needs to begin, say around matter radiation equality or the formation of the CMB, these UFO dark matter particles are now moving slowly enough to act as cold dark matter. Their free streaming length is no longer large enough to erase those small-scale density fluctuations.
That's an incredible simplification. We don't need a new hypothetical massive particle like the WIMP to avoid the smoothing problem. We just need to correctly time the decoupling of a light fast particle.
It is the ultimate demonstration that context matters. The original flaw wasn't in the physics of ultra-relativistic freeze-out itself. It was in the assumption that it happened during the traditional radiation era. By moving it to the reheating period, Henrich and Olive essentially converted a hot dark matter candidate into a successful cold dark matter candidate just by leveraging the vast cooling period that's already built into the Big Bang model.
But this must require us to have some pretty strong constraints on the reheating temperature, the T sub R. How sure are we about the physics governing this era? I mean, we can't directly observe it.
That's an excellent critical question, and the honest answer is that the exact mechanisms of reheating are still highly speculative. They depend heavily on which inflation model you choose. The reheating temperature is poorly constrained, though we know it has to be high enough to produce the particles we see, but low enough that it wouldn't have overproduced gravitational waves, which we haven't detected yet.
So Henrich's work is essentially mapping a specific constraint onto that reheating temperature. They're saying if dark matter was produced this way via UFO, then the reheating temperature must have been in this specific range for galaxies to have formed.
Exactly. They connect the viability of this dark matter candidate directly to the dynamics of the earliest moments of the universe. If the reheating temperature was too low, the dark matter would have been underproduced. If it was too high, the timing might still lead to too much smoothing, though their model handles a vast range of high temperatures quite elegantly. It gives cosmologists a new target for understanding that post-inflationary epoch.
So now that we have a viable, cosmologically acceptable mechanism, this ultra-relativistic freeze-out during reheating, we need to see how it fits into the current landscape. You know, the one defined by the WIMP and FIMP searches.
Yeah.
Where does this particle land on the spectrum of how strongly it interacts?
This is where it gets really interesting. The new research suggests that UFO isn't just a third separate option from WIMPs and FIMPs. They demonstrated mathematically that UFO production is an unavoidable intermediate regime.
Unavoidable, that's a strong word. An intermediate regime. So that suggests a continuum, maybe, rather than three separate islands of theory. How does it act as a bridge between the thermal WIMP world and the non-thermal FIMP world?
Right. WIMPs, as we discussed, are defined by thermal freeze-out. They're heavy, they decouple late. FIMPs are defined by freeze-in. They're often light, and they interact so rarely they never even reach equilibrium. Henrich and Olive's UFO candidate sits right in the middle. Its production is tied to the non-thermal decay of the inflaton, which is FIMP-like, but its decoupling is kinetic, which is like a hot freeze-out particle, just one that then gets a long time to cool.
Okay, so if we picture that standard plot that physicists use, dark matter mass versus interaction cross-section, that crucial map where we search for candidates, where do these new UFO particles sit?
They fall directly below the parameter space that has been so exhaustively tested by the WIMP detectors. WIMPs occupy that region of relatively high cross-sections. Still weak, of course, but strong enough that if they existed in that range, an experiment like XNT should have seen them by now.
And the UFO candidates?
The UFO candidates are specified to interact even more weakly than the WIMPs we've been looking for, though probably still stronger than the most extreme FIMPs.
This directly explains the detection impasse, then. If the universe's dark matter is just slightly less interactive than our detectors were optimized for, it's no surprise we found nothing. We were looking for an interaction strength that was maybe a bit too generous.
That's the bitter reality, perhaps. We spent decades designing these incredibly sensitive experiments that were optimized for what's called the WIMP-IM miracle. The idea that WIMPs produced thermally would just naturally have an interaction strength that made them detectable. The UFO model suggests the dark matter particle is far more elusive than that scenario predicted.
So for the listener, what does imperceptible to Earth-based detectors actually mean in practice for this UFO candidate?
It means that if a UFO particle were to stream through a detector like xenon, the probability of it transferring enough momentum to a nucleus to create a measurable signal is incredibly low, possibly orders of magnitude below the current detection threshold. These particles are ghosts passing through ghosts.
But, and this is the vital part,
this extreme weakness is only for its interactions with the standard model forces. Its gravitational presence remains massive, ensuring it's completely compatible with how galaxies form.
So we have a cosmologically viable candidate that solves the structure problem, and its interaction strength explains why we haven't found it. Like a powerful self-consistency check. But if they are so elusive, what practical guidance does this work offer for the experimentalists? How do we find something that sits below our current sensitivity floor?
And that's the real practical payoff of the theory. The team didn't just propose a mechanism, they provided concrete parameters. They mapped out the precise range of dark matter masses and interaction strengths, the cross-sections that are compatible with the UFO mechanism, while also surviving all the cosmological constraints, like the need for structure formation.
They mapped the exact location of the needle in the haystack.
They did. And this opens up entirely new strategies for detection. Instead of continuing to just push deeper into the WIMP parameter space, that heavier, slightly stronger interacting range, the focus can shift. We can start designing experiments that specifically target these weaker interactions or potentially lower masses that are consistent with this UFO mechanism.
What kind of experiments would that even be? How do you capture a particle that's interacting more weakly than a WIMP?
We might need to move away from relying purely on nuclear recoil signals, which is what the current generation of detectors specialize in. Future experiments might need to focus on detecting particles with much lower masses, maybe in the sub-GeV range, or employing more exotic techniques, like looking for electron recoils in superconducting devices, or even searching for tiny specific signals in the CMB that could be related to these particles' residual interactions.
It sounds like this research really validates the shift toward next-generation detectors that are already being planned, the ones designed to push the sensitivity envelope toward that feebly interacting regime.
Absolutely. It takes the general theoretical push towards FIMPs and gives it a highly specific, cosmologically verified target. It revitalizes the search. It frames a decades-old concept, ultra-relativistic freeze-out, as a cutting-edge, testable solution to the current crisis. It tells us we need to broaden our search strategies.
And the beauty here is that this isn't just swapping one theoretical particle for another. This is showing that a known production mechanism, thermal decoupling, can be adapted. By shifting its context to the earliest possible moment, the reheating era, it generates a cosmologically cold candidate that perfectly explains why our current experiments have found nothing. It's a fantastic example of solving a modern problem with a historic fix.
And it forces us to reconsider the fundamental assumption that cold dark matter must be massive. This UFO dark matter is light, and it was born ultra-relativistic. But because of the cosmic timeline, it behaved as cold dark matter when it mattered most. The key property isn't the mass, it's the speed at the time of structure formation.
That distinction, mass versus speed when structure forms, that seems to be the defining lesson here.
It is, and the constraints they provide are a crucial step forward. It transforms the pursuit of dark matter from a broad, almost blind search across an unknown landscape into a targeted investigation of a highly constrained physical mechanism.
We've covered a huge amount of physics today. We've moved from the initial failure of neutrinos to the decades of failed WIMP searches, all to arrive at this powerful, revived theory. Let's quickly synthesize the timeline for you.
We began with the initial elegance of hot dark matter in the 1970s. That failed the cosmological test because its high speed caused too much density smoothing. It erased the small-scale fluctuations that galaxies need to form.
That failure led us straight to the WIMP model, which required massive, slow particles to preserve those density fluctuations. But the WIMP search has hit an impasse, suggesting those particles are either too weak or maybe just don't exist in the expected mass range.
And finally, Henrich and Olive offer this elegant solution, ultra-relativistic freeze-out, but not during the standard radiation era. They move it to the incredibly high-energy, early reheating era right after inflation.
And that single shift resolves the smoothing problem by giving the particles enough time to cool down before structure formation begins. It lets them act like cold, dark matter. And at the same time, it explains their elusiveness by defining their interaction strength as weaker than the WIMPs we've been searching for.
You know, the value here is that the simplest solution is often the right one. But sometimes that simple solution requires the most complex understanding of context. The answer wasn't some brand new quantum field. It was correctly placing a known physical process into the single fraction of a second where it becomes viable.
It really makes you appreciate the fine-tuning of the universe. The entire success of this UFO theory rests on the dark matter having just enough time to cool down before gravity needed to start collapsing those initial seeds. It brings us back to the contingency of the cosmos.
Well, if you look at the constraints Henrich imposed, the physics of dark matter production and survival hinges on that reheating temperature, T sub r. If that temperature were outside a specific, surprisingly narrow window, or if the duration of inflation had been slightly different, the cooling period might have been insufficient.
So if the history of the universe had unfolded even just marginally differently at 10 to the power of negative 32 seconds, the free streaming length of this dark matter might still have been large enough to erase all the small-scale structure.
Exactly. And it raises a pretty provocative thought. If the timing of these cosmic events, reheating, decoupling, and the onset of gravitational collapse, if they'd been slightly misaligned, structure formation might have been impossible. The very existence of galaxies, stars, planets, and us might be fundamentally defined by this incredibly narrow, razor-thin window of opportunity for particle decoupling right at the dawn of time. Could the whole history of the universe and our very presence in it be contingent on the perfect timing of dark matter particle cooling? That's something pretty profound for you to consider the next time you look up at the night sky.